Okay, let's get started. So today we're going to be doing two problems. The first one will be a normal DP, and the second one will probably be your first introduction to subset DPs. Before I started, I did want to point out one thing, which is that on Moodle, you now have access to both lecture slides and tutorial problems. So the lecture slides will be the slides to the lectures that you've seen so far, the most recent being dynamic programming. But what's more important to us is the tutorial problems. So on Moodle, you can now access the tutorial problems before the actual tutorial themselves. So these are normally released a few hours after Monday's lecture. So if you want, make sure to check out Moodle for that. Anyway, I'll link the problem sets nevertheless, so you don't have to open Moodle and log in and all that. So our first problem today is going to be boredom. Yes, a very common problem for us programmers. Okay, so the problem goes something like this. So Alex doesn't like boredom. When he gets bored, he plays games. He comes up with a game to play. So you're given a sequence of n integers, and the player can make several steps. In every step, you can choose an element of the sequence, let's denote it AK, and delete it. After that, all elements equal to AK plus 1 and AK minus 1 are also deleted from the sequence. This step gives AK points to the player. So Alex is a perfectionist, so he decides to get as many points as possible. You can help him. So we're given as our input n, which is less than or equal to 10 to the 5. And we're also given as our input a sequence of numbers a. Each of these numbers is between 1 and 10 to the 5. So for example, let's just take this final input here, 9, 1, 2, 1, 3, 2, 2, 2, 3. And let's just go through it together. So oops, that's too far. You've seen my previous lesson now. Okay, anyway, let's say we have 9, and then we have, what was it? 1, 2, 1, 3, 2, 2, 2, 2, 3. Something like this, right? And so the idea is that Alex is going to progressively pick numbers from this array. So for example, he might start with the number 3. Now, if he picks the number 3, he's going to get 3 points. But he's also going to delete every single adjacent number to 3. So for example, 3's adjacent numbers are 2 and 4. So every single 2 and every single 4 is then deleted from our array, which means that Alex can no longer pick them now. So so what Alex is trying to do now is he's trying to maximize his score, allowing for these deletions as well. So in this particular case, Alex's best score is to just pick all the 2's like this. After the first time he picks a 2, all the 1's and 3's will be deleted, but then all the rest of the 2's will remain. So he's going to pick the rest of the 2's, and is going to get a maximum score of 10, which you'll find matches up with this output. Okay, so I'm going to give you a couple of moments now to actually think about this question, sort of get your bearings around this question before we go and discuss the solution. So check this problem out. If you have any questions, now would be the time to ask. I'll give you just like a couple minutes to do that. You missed literally nothing. So what we're doing now is we are just reading the problem and sort of getting our bearings for a couple minutes. Okay, so I think we've all had time to familiarize ourselves with the problem now. So let's get into actually solving it. So let's start with one very, very key observation here. Let's say that Alex picks the number AK. Would picking another number AK ever be suboptimal? And by that I mean picking another number with the same value as AK. Would ever picking that ever be suboptimal? Right, exactly. The reason being is that when you pick AK, right, you delete AK minus 1 and AK plus 1 from our array. And now all we're left with is well, the other numbers and also some other AKs, right? So picking these AKs will never actually delete more numbers from our array. So in that case, we might as well just take them, right? Because they're 3 points. You can take them with literally no consequence. That's great. What this allows us to do is it sort of allows us to compress our array into a sort of, into only counting the frequencies of every single number. So for example, this is our original array A. What I'm going to do is I'm going to compress it. And I'm going to make a bunch of pairs. And for each pair, I'm going to store the number and the number of times that it occurs. So 1 occurs twice, 2 occurs 5 times, 3 occurs twice, and just for the sake of this sample input, because I know I'm going to want this later to demonstrate a point, I'm going to add a 5 onto the end here. So adding on a 5. So we'll get this sort of compressed array, so to speak, right? So we've just compressed everything together. And now we can sort of see why this is useful, because when you pick a 2, right, you always want to pick all of them. So if you were to choose 2, then you would just take the product of 2 and the number of times it appears, and then that would be how much score you'll get. So now all we need to do is we need to somehow pick numbers from this array, our new compressed array, so that we never have any conflicting numbers, i.e. we never pick 2 numbers that are adjacent, and we want to maximize our score as well. While we're at it, something that's useful to do is we'll just sort our numbers. So 1, 2, 3, 5 are in ascending order. Since the input, the order of the input doesn't actually matter, well then it doesn't really matter for us if we sort it or not. And sometimes just prescribing an order to something is just going to be very useful for us in our following DP. So, okay, now that we've got this new array, we want to perform some sort of DP on this array. So I'm going to assume that you have some familiarity with DP since we've all done comp3121 before. So would anyone like to suggest an idea for what the state might be for our DP? Okay, well, okay, Afaf says value times count. Okay, so that's not really quite a state, but it is the way it's the way of calculating the score of choosing something, but it's not quite what I'm looking for when I say a state. So when I say a state, I mean some sort of well, it's a state that such that we sort of start from the beginning. We start from some sort of beginning state, which we call the base case. And eventually we'll do recursion on these states in order to reach the end. I think this is best illustrated by going through an example. Jeremy says the remaining AK options available. Okay, that's a really good state. I'm going to actually rephrase that just a little bit. Instead of the remaining AK options available, I'll say the current, I'll say the number of elements that we're up to. So it's sounding like the same thing. So, okay, let me just clarify myself. What do I mean by that? So, dpi will be equal to the max score we can get considering up to the ith number. In this case, our state would be the number that we're up to inside our B array, right? So for example, dp of this one would be 0, 1, 2, 3, right? If we number it. In that case, dp of 2 would be the best score we could possibly get by only selecting numbers from here, right? Not from here, but only selecting numbers from here. The idea is that we're going to start from a base case, which will be dp0, and we're going to work out dp1, and then dp2, and then dp3, and then all the way up until we reach the end. Okay, so let's actually start with our base case, just to sort of solidify this. What's our base case? What should be the value of dp0? Right, so the value should be 2 because we have, value should be 2 because we have 2 1s at the very beginning. Since we're only allowed to pick from here, well, then we might as well take the, we might as well take everything that's here. So we can just write this as 2. More specifically, what we actually did to actually get that value was we took b0.x and then b0.y. So in other words, we took the score of the first thing. Yeah, score when k is 1. Yeah, exactly right. So you're taking the score of the first thing. That's how we generate our base case. Now the idea is that we want to calculate dp of I for every single I larger than 0, right? And then all the way up until n. If we can calculate dp of n, or most likely dp of n minus 1, right? Then that's the final solution. Because what it's saying is that that's the maximum score of choosing from the first n elements. In other words, choosing from all the elements. Okay, so that's our base case. The next thing we need to do for a dp is we need to find a recurrence. What a recurrence basically is a way of trying to calculate dp of I based on some previous values. So the idea is that when you're trying to calculate dp of I, you would have calculated dp of I minus 1, dp of I minus 2, and so on all the way backwards. So now you want to try and use these values to calculate a dp of I. Okay, so let's say we're trying to calculate dpi, which is the max score we can get by considering up to the ith number in B. There are sort of 2 cases here that we need to consider. Does anyone like to guess what those 2 cases are? Yeah, exactly right. So there are 2 cases. The first one is case 1. We don't add bi. And case 2, we do add bi. And of course, these are the only 2 cases, right? So if we can find the value of dpi if we don't use bi, And then we find the value of dpi. If we do use bi, then we can just take the maximum of the 2 to find out the value of dpi. Okay, so let's actually start with our simplest case here. If we don't add bi, what does dpi equal to? What should we set dpi to if we're choosing not to add bi? dpi minus 1, exactly. Why is that? Well, since we're not taking this value, well, we might as well take the value of everything before, right? Because we've already calculated the best score of using everything up to I minus 1. And since we're not using bi, well, then these two are then equivalent. Okay, now we move on to the slightly harder case here. How do we calculate dpi if we have to take bi? Again, you might have to two cases here. Would anyone like to guess at what the two cases are, first and foremost? Right, so Jeffrey says we can directly add it in, or we can't. Sometimes we can't actually add bi because, well, we can't add bi because the previous one might be 1 minus of bi. So you need to handle that case separately. Our Fav says bi equals the max of dpi minus 1 and ak plus dpi minus 2. All right, that's really good. So the first case, your max has 2 arguments. The first argument is case 1, right? And what your second argument is dpi equals b of I plus dp of I minus 2. Okay. So what's it actually, yeah, what I need to do here, it's not just b of I, but rather I need to take the entire score associated with that number, right? So I need to do bi dot x times bi dot y. And that'll give me the score of the number bi. Okay. So we're going to do that plus dpi minus 2. Do we always want to do this? Do we always want to take 2 behind? And we kind of already answered this question in the chat. Do we always want to take dpi minus 2? Or is there some case where we might want to take dp this score plus dpi minus 1? Yeah, Felix is exactly right. So we only want to do this if the 2 elements are 1 apart. For example, if we're looking at this 5 and 3 here, well, dp of 5, if we want to take it, we can also take 3 as well. So we can actually, if they're not 1 apart, then we can take the dp of I minus 1. If they are 1 apart, then we need to skip the last one and then take the dp of I minus 2. So this code should look something like this. If b of I dot x plus 1 equals bi, then we take then we do this. Otherwise, we do this. Okay, great. So that pretty much sums up our entire solution. So now all we need to do to actually finalize our value of dpi is to take the max of this value here as well as the maximum of case 2, and that will give us our value. So let's actually work through the sample data just to make sure that we're understanding how this dp works. And then we can start coding it up. So let's say we've already generated this B array here. I'll go into detail about how to actually do that when we do the coding. But for now, let's just assume that we magically have this B array. Now we want to do our DP. So this DP is going to mirror our numbers in that it's going to be a 1D array with n elements in it. Now our base case is the score of the first one. So this is 2. Next, we look at this here. If we don't add BI, well, then we can just take 2. If we do add BI, well, this is actually this equal to 1 plus 1. So we have to take I minus 2. So we need to go into this case here. dpi equals 10, this score, 10, plus I minus 2. In this case, we don't actually have an I minus 2. So we just have to be careful when we implement to make sure we handle this case. In reality, when we're actually looking back here, we don't exactly want dpi minus 2, but we want 0, right? Because there's no element behind there, so we can just ignore this entirely. So this is just something we'll deal with in implementation, but I won't really deal with in theory. So this value is 10, right? Maximum of case 2 is 10, case 1 is 2. So we take the max of them both. Okay, this case here, 3 is 1 plus of 2. So, okay, so once again, yeah, so 3 is 1 plus of 2. So once again, we'll look at, we'll look at, wait, did I swap these around? I think I swapped these around. So if it's not equal, then I can take I minus 1. If it is equal, then I take I minus 2. Yeah. Okay, so here, if we don't add it, then case 1 is 10. If we do add it, then since 3 is 1 plus of 2, then we need to look 2 back. So you get 2 plus the score of this, which is 6. So you get 8. However, case 1 is larger, so we should take 10 instead, which would get from considering this DP over here, or this DP value. Final one, we have this 5 here. Once again, we look at the previous one. If we don't add BI, then we'll just take the max of this. So case 1 is 10. Case 2, this time, it's actually not equal to the previous one, in which case you can actually take the DP value of the last one. So in this case, the last one is 10. So add on a 5 onto it and get 15. So case 2 was 15, case 1 was 10. So we take 15. And our final answer is 15. So we get the final answer by checking DP of n minus 1. In this case, this 15 is generated by this 10 getting 2 5 times and then getting 5 1 time. Okay, does this solution make sense to everyone? If there's no problems, I'll begin coding. Okay. The first thing I'm going to do, I'm going to put our everything we've got here at the top of our code. Okay. Next, all we need to do is we need our header libraries. So TSTIO has printf and scanf. iStream has cin and cout. What else do we need? We're going to need vector today, which we learned about last week. We're going to need algorithm, because we're going to need to perform a sort at some point. And we're going to need utility as well. So utility is going to provide us with pairs. Okay. All right, that should be all the header files we need for this problem. If there's any more, we'll make sure to add them to the top. Let's add a structure name using namespace std, so you don't have to write std : everywhere. Okay. So our input is given as a single integer n followed by n inputs. So we'll just scan that in. And we'll scan in our sequence as well. Now what we need to do is we need to generate our B array, right? Because that was pretty important. That was a pretty important part of our DP. So the way I'm going to do it is like this. I'm going to first sort A plus N, and then now I'm going to declare a vector called B. So this B, it should not be a vector of ints, it should be a vector of pairs. And this B is going to store a bunch of pairs like this. So the idea is that after we sort A, all the same numbers will be next to each other. So it'll look something like this. And so what I'm going to do is I'm going to loop over A, and then for every single new number I see, I'm going to push that number onto the back of B. And if this number is the same as the last one, I'm going to update the count of the last one. So it's going to look like this. If B is empty, or b.back.second does not equal A of I, b.pushback A of I. Else, b.back.second, oops, it should be first, b.back.second plus plus. I need to push it on a pair, so push it on AI and 1. Okay, so what is this doing? If B is empty, or if the last element in B doesn't equal to AI, we'll push on AI with a count of 1. If the last element does equal to the AI, then we will increment the count of the second one by 1. Okay, so that should generate our B array. A good thing to check. So let's print out our B array. And let's give it some sample input to run on. Going to add that 5 onto the end, and then let's try and run it. Okay, so getting some warnings here. Type in, right, okay, so I'm trying to print out a pair, but this is an integer. So what I really want is bi.first, and I want to print out the whole pair. So let's get some brackets in. bi.first, bi.second. Okay, so I'm actually getting some extra things in here that don't look quite right to me. And the reason is because I'm looping through n, not b.size, right? So I'm looping too far, so I should be using b.size here. And this looks more correct. So great, we've generated our B array. One thing I'm going to do before we move on is we have a lot of firsts and seconds around here, which we're using to access our pair, but I don't really like typing that much. So instead what I'm going to do is I'm going to declare hash define x as first and hash define y as second at the top of my code. And this is going to replace every x with first and every occurrence of y with second. So now I can shorten my code a little bit by replacing first with X and second with Y. Great. So it looks like we're still working. Okay, I missed okay, so I missed one. Afaf says, if we sort after we enter into the B array, would it be faster? Well, we can't actually sort after we enter into the B array because we're relying on the fact that A is sorted to generate our B array, right? So we're relying on the fact that all of these are adjacent to each other in order to keep pushing on to the back of our B array. So yeah, we need to sort A first. And notice that after we sort A, our B array was also going to be naturally sorted. So we don't actually need to sort our B array afterwards. So hopefully that answers your question. Let's move on. So would it be faster to use a map for B? Let's map this one. So, okay, one thing at a time. Would it be faster to use a map for B? Yep, yeah, that's definitely one way you could do it. So we could, instead of storing the actual, this thing inside B, we can just store it inside a map. It's probably about the same complexity if you use an unordered map. So this is fine. B is just a frequency, so we should be able to sort it later. I don't quite understand. So after we generate B, it's already in sorted order. We have 1, 2, 3, and 5 already in sorted order. So I'm not quite sure why you would want to sort it after. Sorting it at the start. Okay. Well, the problem is that if we're not using maps, right? If we're not using maps, then each time we find a number, we can't actually just insert it onto the back of B, right? So we have to actually look through our B to find the specific number and then increment that one by one. So yeah, that's going to lead to some extra time complexity. So we don't want to do that. Okay. At the end of the if you do want to use the maps, that's totally up to you. That's your choice. But we're going to use pairs instead for today's lesson. Okay. So next thing you want to do, let's declare a DP. So DP of n. Let's set our base case. So DP of 0 equals this thing here. So b0.x times b0.y. Then let's do through. So we're going to start at 1 because we know we've already done our base case. So we don't need to calculate DP of 0 again. Okay. So let's take the two cases here. Case 1, don't add bi. So case 1 would equal to dp of I minus 1. Very straightforward stuff. Case 2, add bi. So we'll declare case 2 as 0 here. And now we can just copy over, or actually already have copy pasted over here. Let's just copy paste over our if cases that we worked out earlier. So if bi minus 1.x plus 1 doesn't equal to bi.x, then we want to take the I minus 1. So is that, we'll let case 2 equal this rather than dp. Otherwise, we'll take case 2 equals this. When we were doing our walkthrough, that we actually encountered something here, which is that I minus 2 isn't always available. So if I minus 2 isn't available, we don't want to actually set this case 2. So all we need to do is check if I is larger than or equal to 2. If I is larger than or equal to 2, then this will have a value. If I is not larger than or equal to 2, then we need to have our final case here. So if it's equal and I is less than or equal to 2, then case 2 equals just the score. Remember, we sort of added a 0 onto the end, so we can just ignore that and just leave it as the score. Okay, so that should do it. Not the most prettiest of codes, but it should get the job done. And now dpi It's just the maximum of these two cases. So that should calculate the value of dpi from 1 all the way up to n minus 1. And so our final answer will be dpi minus 1, n minus 1. Okay, that's right. Let's see if it works here. So we're expecting the answer 15, and we actually got the answer 15, which is great. Let's run it on some of the other sample inputs from Codeforces. 2, good. 3. So yep, and sample answer is 4. And this one, before we actually modified it, so we should be expecting 10. Great. So it looks like for these sample inputs. Okay. So this is the code so far. Are there any questions? Can anyone see anything wrong with this code? Because off the top of my head, I know there's one thing that is wrong with this code. Let's try submit it and see if we actually get full marks. So let's try to see how it fails, or if it fails at all, really. And we got a wrong answer on test 3. So we could look at the test inputs, but it's not really a good idea since in real contests we don't have access to those inputs. So we're going to have to try to think of something else here. Okay, so as a hint for what's wrong, I'd like to ask you the following question, which is, what is the maximum value that you might have to output? So looking back at our problem statement, what's the maximum value that we might have to output for any given input? Jeremy, you've caught on. Very good. We're going to need a long, but I want this question answered first. Jeffrey Yang says 10 to the 10. That is correct. So because you can get 10 to the 10 if we have 10 to the 5 numbers, and also every single number is 10 to the 5, which means that we would pick every single one of those numbers. So that gives us 10 to the 10, which is about 10 billion. Yeah, and integer can only store up to 2 billion. So that's not going to be enough. So we're going to need to use longs instead. So now we just have to make sure that anything that stores a score uses longs. So let's type def long as LL. And then now our DP is going to use longs. Let's make sure we print it out as a long. These cases are also going to use longs. We don't want them overflowing. And you might as well just use longs for B as well. That way we can be sure that there's no shenanigans going on with type conversions when we are multiplying these two ints together and then adding them with a long. Okay, I think that should be it. Let's compile it one last time to make sure we don't get any warnings. Great. And then let's try to submit it one more time. And fingers crossed accepts. Wrong on test 4. Okay. GG, indeed. Okay, so we have some extra bug that I haven't considered yet. So let's try and look through it. So first thing we're going to do, we're just going to stare at our code for a little bit and see if anything wrong immediately pops up. So you guys feel free to do that also. Case 2 needs a max. Does it need a max? What do you want a max of? No, I would say that it doesn't need a max because if it's not equal, then we're going to take the previous one. If it is equal and I larger than equal to 2, then we're going to do this. If it's equal but I is equal to 1, then we're going to do this. None of these require maxes. All of these are just the correct answer for case 2. So I'm not too sure about that argument. Felix seems like he's got it. Yeah. So so we're looping from I equals 1 to n here, but I made the exact same mistake that I did earlier in the lesson, in that we shouldn't be actually looping to n because the size of b isn't actually n. So we should be using b dot size here instead. And so at the very end here, we also use b dot size minus 1. So let's run this again, make sure it's producing correct output. Great. Honestly, I'm not sure why it worked before, but I guess we just got lucky and was going a lot of values which were 0, so it didn't actually change our DP. But yeah, let's use the correct values. Thank you very much, Felix, for spotting that. And let's try to submit again. Hey, let's go. All right, so that's the code for the DP. Are there any questions about this problem? Okay, excellent. Let's move on to our next problem. This problem is going to be called pebbles. So as just a sort of warning here, this problem is going to be using a subset DP. This is going to be very challenging if it's the first time you've sort of coded up a subset DP before. So during the sort of explanation, I'd be happy if you were just to be able to get the gist of what's going on. And then during the coding, we can sort of figure out any sort of small complications that come along the way. Okay, so the problem is going to look something like this. I'll link it in chat as well. You're given an unlimited number of pebbles to distribute across an n by n game board, and n is smaller than equal to 15. Immediately, you should be have some sort of warning here because n is very, very small, which seems to suggest some sort of exponential solution. Not always, but it's just sort of a hint. So you have an n by n game board where every square has an integer between 1 and 99. The integers of a given board may not be unique. So for example, we have this 6x6 board here. So what we're trying to do is we're trying to find some sort of valid place of the pebbles so that these two conditions are met. The first one is that you have at most one pebble on any given square. And the second one is that no two pebbles are placed on adjacent squares, adjacent being horizontal, vertical, and diagonal. So for example, if I place a pebble on 55, I can't place a pebble on 81, 43, 39, 20, or 11. But I can place a pebble on 15, or 17, 9, or 58, and so on, right? So pebbles cannot be. The goal is to try to place these pebbles so that you maximize your score. So the input's going to look something like this. You're getting a bunch of squares separated by new lines. And we want to print out the maximum score for every single one. Okay, so I'm going to give you a couple of minutes to think about it. Once again, to familiarize yourself with the problem. During this time, I'd like you to think about inefficient solutions. So we'll start by thinking about solutions of any time complexity, and we'll see where that leads us. And afterwards, we'll try and bring it back into a nice DP. So for now, read the problem and try to think of any solution that could work. I'll give a couple minutes for that. So if you come up with any solution at all, make sure to post it in chat so I know. Okay, so R5 suggests a solution. Go through every permutation and find the maximum sum. Great. So this is the brute force solution. We're going to test every single case and we're going to find the sum of each of them. Okay. Question, how many cases will we have to test? Two to the n squared, exactly right. So right, to the n squared. Sure. Yeah. So you can say subset or permutation. When I said permutation, I sort of meant permutations of zeros and ones. Oh, I guess, yeah. Okay, fine. Subset is probably the better term here. So we're going to test every single possible subset, and there are 2 to the n squared possible subsets. All right. And for every single subset, we're going to need to do n squared to actually sum them up, right? So we get a solution of n squared to the n squared. This is fast enough. Fav says no. That's exactly right. So if you sub in n equals 15 here, well, we get 15 squared times 2 to the 15 squared. And that is us about 10 to the 70, right? 10 to the 70 is obviously way, 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 way too big. So this solution is going to time out. All right. Okay, so that's the brute force solution. It's not going to work. So we need to speed up our solution in some way. Okay, so let's try to apply a DP here. So I'm going to actually start with a tentative state for our DP. And then hopefully we can try to refine it so that it becomes a little bit better. So let's say, let me draw a grid real quick. There we go. That's what I wanted. Okay. So let's say I had a state called dp of I, where I is the row that we're up to. So kind of like before, how we were up to a certain element, this time we're going to store a row. So dp of I is equal to the maximum score by only pebbles in the first I rows. Okay, this is going to be our tentative state. Is this state enough to make a full DP or make a recursion? Or do we need extra information in our state? What do you guys think? In other words, can you use the values of dp I minus 1, I minus 2, I minus 3, etc. to calculate the value of dpi? Right, Arthur's absolutely correct. This is not enough. You're going to need the position of the pebbles, right? So for example, let's say I know dp of 2, right? Or dp of 1 rather, since we'll index these rows like this. Let's say I know the dp of 1. This doesn't actually tell me about the dp of 2 because I don't know how the pebbles are placed, right? I don't know if I can placement of pebbles because I'm not sure if the best solution for dp1 involved having pebbles like here, for example. Yeah, I'm gonna make that valid, but yeah, I don't know if the solution for one ended up having like a pebble here. So what I need, as well as the row that we're up to, is, as Arthur says, we need the positions of the pebbles on the previous row. So let's actually update our state. So instead of just having I, we're also going to have B. So dp of IB is equal to the maximum score of placing pebbles in the first I rows, with the last row having pebbles B. And so what B is it's going to be a bit set. So can you imagine B? It will look like a bunch of zeros and ones. Like that. And so these zeros and ones will represent whether a pebble is placed or not. So for example, this particular B might that we have row I with pebbles 1, 0, 0, 1, 0, 0, 1. In other words, we place pebbles here and here. Okay. So this is really nice. Now we have this new DP. How can we use the previous DPs to calculate DP of I and B? So let's say you had for every single DP I minus 1, B for all B. Let's say you knew all those values. How could you use those values to calculate DP I comma B? So before I start, let's actually do an example here. So let's say we're trying to calculate DP of 3, and we'll use 0, 0, 0, 1, 0. Okay? So in other words, we're trying to calculate the maximum score we can get by placing pebbles only in the first 3 rows, or up to the first 3 rows, and with a final layout of 0, 0, 0, 1, 0. Okay? So we're trying to look at DP values of DP I minus 1. So what values of, so we're going to need to do something involving DP I minus 1 and some B's, okay? Which B's might we want to consider here? Right, exactly right. So for every single BJ, we'll pick the maximum pebble placement on row I, such that there's no conflict between this 0, 0, 0, 1, 0 and the previous row BJ. So for example, if we were to just list them all out, actually, you know what? I'll ask you guys to list them all out. So what are some examples of the possible stone placements on the previous row, given that we have a current stone placement of 0, 0, 0, 1, 0? 1, 0, 0, 0, 0, and 0, 1, 0, 0, 0. So those are the only two stone placements. So this corresponds to a stone here, and then a stone here. Notice that we can't have any stones over here because that would conflict with our one stone over here. So we only had these two options, right? So in this particular case, if you were to calculate of 3 and 0, 0, blah, 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 then we just take the max of dp of 2, 1, 0, 0, 0, and the dp of 2, 0, 1, 0, 0, 0. And of course, we need to also add on the sum of our current one. Because we'll take the max of the previous one, and then we also need to add on the pebble sum of this. In particular, we'll add on the pebble, the score under this particular pebble. Okay, is everyone convinced that this is the correct way to calculate, at least for dp3 0, 0, 0, 1, 0? Are you all convinced that this is correct for calculating this dp state? I'd like a couple more answers before I move on. But can that solve the problem? What if the placement of pebbles on the row 3 affects the placement of pebbles on row 2? Well, that's the beauty of it. So that's the beauty of dp. So what we're going to do, we're not only going to calculate the dp of 0, 0, 0, 1, 0, we're going to calculate the dp of every possible placement of pebbles on row 3. So this is what we're going to do. I'll sort of build it up from the beginning. So first off, we're going to start with our base case at, what is this? This is I equals 0, right? So at our base case, well, dp of I and b is just equal to the sum of the scores underneath our pebbles with placement b, right? Okay, so we can now calculate dp of ib for all I equals 0. Now, when we move on to dp of I equals 1, we can calculate every single dp of I equals 1 and for any placement of b as well. So we're going to do it for all placements, right? So in that way, we have every single placement possible with row I. We guarantee that we know the correct answer for every single possible placement. Now, once again, we can use that to build up our solution to row 2, and then row 3, and then row 4. In each case, we're not actually concerned with the placement of the next row, only the placement of our current row. Does that sort of make sense why we don't need to consider the how row 2 might affect row 3? What we're saying is that we're calculating a placement, sorry, we're calculating the dp value for a very specific placement of row 3, and then we're only going to use the values of row 2 to check that. Okay, let's go for an example then, just to make this clearer. So let's start with a very, very small, very small grid, right? So this will allow us to calculate our answers. Okay, so recall that dpi is the maximum score of placing pebbles in the first I rows with the last row having pebbles b. Okay, so let's look at dp of 0 and 1, 0, dp of 0 and 0, 1, and dp of 0 and 0, 0. These represent all the valid placements of pebbles on the first row, right? We can't have 1, 1 because that would not be valid. Okay, let's make up some values here. So let's go 1, 4, 2, 3. Would anyone like to give me the values of these first 3 base cases? 1, 4, and 0. Perfect. Okay, so using our base case, we can work out the DP values for all I equals 0, assuming that the B is valid. Okay, now let's move on to the row 1. So once again, row 1, we're going to calculate the value for every single possible placement of pebbles. So that's 1, 0, 0, 1, and 0, 0. Once again, we don't really care about the pebbles in 2 because we're just calculating every single possibility, right? Okay, so 1, 0. Well, what are the values of bj in this particular case? In other words, what values of pebbles in row 0 should we consider when we're calculating this DP here? Just 0, 0, right? So we'll take the max of 0 and the sum of the pebbles under here, which is 2. Or rather, we'll add them together, not take the max of them. Okay, for 0, 1, again, the only thing we need to consider from row 0 would be 0, 0. Everything else conflicts, right? So we look at 0, 0, that has a score of 0, and we add on a 3 to it, so we get the answer 3. Finally, we look at DP 1, 0, 0. In this case, now we actually have options now. We can look at DP 1, 0, since it doesn't conflict, and we can look at 0, 1, because it doesn't conflict. So the max of these two, well, the best we can get is 4. So DP, we'll get 4, and we'll add on the pebbles under here, which is nothing. So in that case, we'll get 4 as our final answer. And finally, to wrap up and get the final solution, because remember, we're trying to get the best possible score out of the whole thing, we're going to take the maximum of all of these. I was going to look at every single possible ending placement for the final row. I'm going to take the maximum of them to get our final answer. In this case, the answer is 4. So our score is equal to 4, which is, ends up being placing 1 pebble here. Does this sort of clear up your answer, Afaf? Okay, excellent stuff. Okay, so this is going to be the solution. This is going to be a solution, or one way that we can apply DP to this solution. So the next thing you need to do now is you need to check whether this is actually going to run in time or not. So how many states are there? So to calculate this state, we're going to look at the number of values for I and also the number of values of B possible. Okay, so Jeremy says 2 to the n on 2 times n. Okay, so I assume your n will come from the rows, right? But why 2 to the n on 2? Where do you get this 2 to the n on 2? Okay, let's change the question a little bit. How many different placements are there for a given row? Right, okay, so you likely only have a maximum of half the number of columns filled with bubbles. Right, so that's fine, but it's not equivalent to taking 2 to the n on 2. So yes, valid configurations, it's not going to be 2 to the n, right? So normally, if you ignored the validity, it would be 2 to the n, because every single thing in your row could be either a pebble or not a pebble. But we can sort of bound that a little bit, because we know that not every single pebble is going to be, or rather, not every single placement is going to be valid. So we only want to try to consider the valid placements. Okay, so this is a very noble idea. It's a very good idea, but in practice, it becomes a little bit difficult because it's really hard for us to actually iterate over only the valid pebble placements nicely. So in reality, we'll just leave it at our upper bound of 2 to the n. So our states would be n times 2 to the n. Okay. What's the complexity of a recursion? To answer that question, we'll have to answer how many states we might have to look back from the previous one in order to determine our answer. N squared? Not quite, because at a specific I and B, you have to look through every single Bj, where Bj is a valid placement of row I minus 1 that doesn't conflict with the current row, right? So once again, using the same upper bound thing that we did before, how many values of Bj might there be? You can ignore the fact that they have to be valid. Yeah, so if we just ignore the fact that they're valid, then there are 2 to the n. So once again, when we calculate our complexity, we'll get n times 2 to the 2n. And that'll be our final complexity. Does this run in time? Okay, I'd like you all to justify your answers. So sub in the 15, and what number do you get? Okay, I'm not sure where the times in tube is coming from, but if we sub in 15, then we'll get 15 times 2 to the 30, right? And so this would give us approximately, I think it's 15 billion or 16 billion. Yeah. So this will not run in time. You guys are correct. Okay. So okay. So let me think about what I want to do right now. Do I want to explore the full solution, which might be very tricky, or do you just want to implement this one? You know what? Truck it. Let's go for the full solution. Okay. So as we mentioned before, this isn't going to be fast enough. So we are going to need an even faster solution. Okay. So I'm going to copy over my board here. I'm going to suggest a really wacky idea. So we're going to actually borrow an idea that we sort of used for the previous one, which is that for a given row, we don't actually care about like the rows that are like 2 above it. We only care about the row, like the previous row, right? The placement of these ones don't really matter. We're only going to check the DP values of the previous row in order to inform us how to do our current DP. Let me suggest another possible DP state. So DP of I, so instead of doing by rows, we're actually going to do by squares. So what we're going to do is we're actually going to go through this grid in order of squares. So we'll start at this one. I'm going to go from left to right, top to bottom, sort of like you're reading it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, right? And this is going to be denoted by yx. Okay, so dp of y and x is, and also something else, and we'll work out what that something else is in a little bit, is equal to the maximum value by only placing up to yx. Okay. In other words, let's say we're looking at the dp of this particular cell here, then dp of this cell is equal to the maximum score we can get by only placing pebbles in this area here. Okay, so just like before, when I asked you, since a row only cares about one thing, and that's the previous row, let's say I'm considering whether to add this number or not. Which cells that we've processed before would be relevant in making this decision? Up, left, diagonal up, left. Okay. So we've got a bunch of very similar answers. So we have, okay, this is a little hard to read, but yeah, okay. I think the general consensus is these three, right? Are you missing one? Is there one more thing? Is there one more cell that we care about? Diagonal up, right? Thank you. Somehow everyone missed that. Yeah, that's really amazing. Because remember, the squares we've processed is actually this part here. Yep. So this one is actually included in that. So what I'm going to do, I'm going to do something very clever here. I'm going to include the placement of the last n+1 squares in my state. So let me update this. dp of yx is equal to maximum value by only placing up to yx with the final placement being b. Okay, so let me explain this just a little bit more with an example. So for example, if b were to equal 0, 0, 0, 1, 0, 0, 0, right? This time b is n+1. I should actually make that clear. Being b, with the placement of the last n+1 squares b. Okay, so if b were equal to 0, 0, 0, 1, 0, 0, 0, then y and if y and x were equal to this square, then what we're calculating, dp of y, x, and b, would be equal to the best possible score we can get by placing pebbles only in this area and guaranteeing that our pebbles look like this. So 0, 0, 0, 1, which means there's a pebble. I'll denote this with a 1. 0, 0. Let's make this a little more clear. I'm going to put a 1 here at the end. And so that 1 is going to correspond to this one right here. Okay, so you can see how this bit set of length n+1 is going to map to the last n+1 squares before our current square. Okay, excellent stuff. So here we're going to do So one more thing, I just checked my notes, just make sure I wasn't missing anything. So next thing we want to do is we also want to define stuff for invalids. So let's say that dp y, x, and b is equal to 0 if b is invalid. So in other words, if like this b were to give us something like 1 and 1 here, which is an invalid b, then we'll just set the dp of that to be equal to 0. Okay, so that's what our dp state is going to be. And this time, we're going to be doing something just a little bit different for our recurrence. So for the first question, what we did is we sort of looked back to get our solutions. So if we looked at our previous dp, you can see that we calculate the dp of I based on previous values of dp that we've already calculated. So this is sort of what we call a look back dp. So the thing that we're going to do differently here is that instead of looking back, we're going to push forward. So how this is going to work is that we're going to have a dp that we've already calculated. So for example, we'll have some sort of dp, and we know that the answer is correct for that one. And then we're going to calculate the dp for future values and then push that result to the future values instead. So what this is going to sort of look like, if you can imagine, we use the push forward example, push forward method for the first question, it would be like calculating the base case and then using the base case to calculate the values, potential values of this, of the next two, this and this. And then we look at this one and then using the value of this to calculate the potential values of future states and so on, right? And we just keep building this up. And each time we arrive at a value, we know that that value will be correct. And we can use that to correctly calculate the state of the answer for future states. So that's what it means to have a push forward sort of DP. Okay, let me clarify this by going through the recursion. So, okay, so let's say we have our current state of DP y, x, and b, right? Let's say that we have the solution to this right now. It's not that we have the solution to the previous ones. We have the solution to DP y, x, and b. What are some future states that we might want to consider after this one? So in particular, there are two. There are only two that we really care about. And they both have to do with how we fill in the next square. So we have that DP y, x, and b. So let's say that that refers to this sort of segment here, right? So let's say yx is this square, and then the b bit set refers to this sequence of numbers here. Okay. Let me ask you this. How many ways can we fill in the next square? So the next square along would be this. Two, exactly right. What are the two ways? One or zero, exactly right. So what we can do is that we can actually use the DP value of this state in order to calculate a future DP value of this state. And so there's going to be two cases. So once again, we're going to use two cases just like the previous one. So case one, we don't take the next square. And case two, we do take the next square. Okay, great. So case one is going to be easy, all right? So just like before, how our case 1 was easy, when we don't take the next square, then dp of ny and nx, and I'll take ny and nx to represent the square that comes after y and x. Then the dp of this, and then b bit shifted by 1 equals dp of yxb. So what does bit shifting by 1 mean? Well, if we have a bit set that looks like this, well, then bit shifting by 1 means that we move everything to the left by 1. So what this means that this gets deleted and we add an extra 0 onto the end. So in other words, what we're doing here is, if you can imagine, if just assume that this is somehow valid, if our original bit set looked like this, right? Bit shifting it by 1 would mean that we delete the first element and we add a 0 to the end. And so that corresponds to the next state, right? We go to the next square and we take a 0 because we don't take the next square. So we add a 0 onto the end. All right. Next, we have to deal with case 2, which is to take the next square. So this one is a little bit tricky. First things first, can we always take the next square? Or is it sometimes the case where we cannot take the next square? It depends on B, exactly right. So let's make up a sample B here. So in this case, we can't actually take B because, well, we have a 1 here, right? So it can't actually take the next square. So first things first, we can only do case 2 if our bit set allows it. And remember what we did earlier in working out which 4 adjacent ones matter. So in deciding whether we can do this, we need to consider whether any of these 4 will actually, conflict with our current one. So dp of ny nx. Okay, so only do this if 4 adjacent are 0. So the 4 adjacent ones being the ones that depend on it. Okay, so if they are all 0, which means that we can take the next one, then ny and x, and then b bit shifted 1, or 1 bit shifted n equals dp yxb plus the score of yx. Okay, so what did I do here? So I'm using some bit shift magic again. So here I'm using b bit shifted by 1. So again, that deletes from the beginning. That deletes from the beginning and adds a 0 to the end. But this time I'm also ORing that with 1 bit shifted by n. So you can imagine a 1 here, and it gets bit shifted n times to the left or to the right. So we end up with this. And then when I OR it with our previous b, then this becomes a 1. So in other words, I did the same thing as before, but this time, instead of removing the last one and adding a 0, I added a 1 instead. Okay, and so that's going to give us our result for the next one. Okay, so yeah, let's actually write up an sort of outline for this code. I think in the interest of time, we won't code this up, but I'll write up an outline so you can get an idea of how it works. So okay. So basically the idea is that int main scan everything. Oops. And then what we're going to do is that for every single square and for every single bit value b, we're going to calculate the future squares. So our main for loop is going to look something like this. This might not be very visible, so I'll uncomment it so it looks a bit nicer. So for each square, and then for each bit value, and the way we can do this is by just going from 0 all the way to 1 bit shift n plus 1. And so that'll consider every single permutation of placements for the last n plus 1. So if that's the case, so we'll calculate the next square. And what we're going to do is we're going to just grab what we got before and just copy paste that in. So this will be stored as an array. You can imagine that somewhere up top we have int dp of 15 by 15 by 1 bit shifted by 16. So this would be 2 to the n plus 1 right here. And so dp of this is equal to dp of y, x, something like that. And then if the 4 adjacent squares are 0, so the 4 adjacent squares to ny and nx are 0, then we can also do this second part as well. So dp of this equals the dp of this of our current one plus the score of ny and nx. Okay, and so this is just going to go over every single cell, and it's going to go over every single possible placement of the last n plus 1, and it's just going to calculate future states. One more thing that we want to do is we want to actually take the max of this and the new value, because it's possible that we reached this new state from some other way, and then that way had a better score than the one that we're currently considering. So we should always take the max of these two. So we once again take the max of this and that. Okay, so that completes our DP. And just as a final question for everyone, how do you think we can extract the final solution from our DP? It's not as just simple as just looking at one value. We might have to aggregate the results across multiple values. So how do we get the actual final answer, i.e. the maximum score we can get by placing pebbles in all of the squares? Right, exactly. So we'll consider all of dp n minus 1, n minus 1, and we'll consider all possible b values. So all you need to do is we'll loop over every single possible b value of the last square, and we'll take the maximum of all of them. And so that will give us our final answer. Okay, very good. Now let's look at the complexity of this. So, yeah, n minus 1 rather than 14, because n isn't always equal to 15. Okay, let's look at the complexity of this. How many states are there in our DP? And a really easy answer is to just look at how our array is defined here. Because each element in our array is going to represent one state. So how many states do we have? N squared to the n, exactly right. The n squared corresponds to the square. The 2 to the n corresponds to the placement of the final n plus 1 bits. Okay, so the state is n squared 2 to the n. And our recursion, we can see that it's actually just order 1. So this thing is order 1. Checking the 4 adjacent squares is just order 1, right? Because you only check 4 squares. And doing this is also order 1. So our recursion is order 1, and our final complexity is equal to n squared 2 to the n. Is this fast enough? Can someone sub in the numbers and tell me the answer? Right, so 15 squared times 2 to the 15 is equal to about 7 million, which will definitely pass in time. Excellent stuff. Okay, so that's the solution to the DP. Unfortunately, we didn't have time to code it up, but I hope at the end of it, we got an idea of at least the gist of how to use bits in order to do a bit set DP. Are there any final questions about this one? Can I check a paste of this online? Yes, of course. Okay, so I'm going to do that while I set up the breakout groups. So while I'm doing that, you guys can take a break, and then when you come back, okay. First off, let's answer Jeremy's question. Would our row-by-row solution have actually worked? It would have worked except for one thing, which was the time complexity. So yes, it would have worked, but as we calculated, our time complexity for that one was, I think it was n times 2 to the 2, in which case that would be too slow. But other than that, if our n was sufficiently small, that would have been absolutely correct. Okay, so I'm gonna break you up into breakout groups. I'm going to assign randomly, and what I'm going to do is you can move to the group that corresponds to the question that you're currently working on. And I'll also get those codes uploaded onto Pastebin for you guys. All right, bye, Felix. Yeah, so once you're in our breakout groups, feel free to work on the problem set. Okay, you should be able to move to the room matches the problem. You're welcome to stay for last week's problem as well. Like, I can help you on that as well. But that's up to you. So I'm happy to help with last week's problems, with this week's problems, or the exam if you have questions about that. Yeah, so you guys just did a contest with 5 questions in it, so I can help you with that.
Actually, if you have the time, can you just can you go over the question we just did again, if possible?
Okay, but uh, I'll leave that for, I'll check for other people's solutions, sorry, questions first.
Fair enough.
Okay, Jonathan fell asleep, so he's going to catch up here. Okay, just give me a second to upload the pasting solutions, and then I'll have a look at your questions. Okay, so are there any questions about the problem set first? Jeremy, what problem are you up to, just out of curiosity? All right, fair enough. Okay, well, if that's the case, we have no problems yet. I guess we can have time to go over the DP solution again. So, okay, well, firstly, let's ask a follow-up here. Which DP, which part did you want to clarify further? So we went through a couple of solutions, the brute force one, the by rows one, and then the by squares one. So which one do you want to learn a little bit more about? And same goes for you, Jonathan, if you are even awake at that time to know what I'm talking about.
So for me, it would be both the second and the third one. So like specifically for the third one, I just didn't understand as to why you had to consider why you couldn't just take DP of the last number, why you had to look at everything. So
Okay, yeah. So wait, so you're asking why isn't B just one number?
um
So
uh so the final answer, you we had to look at DP of n minus one comma n minus one. So we have to look at, say if n was 15, then we have to look at dp of 14, 14, and then p to find the
yep.
best one. Why couldn't we just look at the last number?
So are you saying the largest number of B?
Yes, so why couldn't we look at dp of n minus 1 comma n minus 1 rather than like everything from 1 comma 1 to n minus 1 comma n minus 1?
We're not doing that though. So to get our final answer, we're only looking through B, which is the final bit set.
Okay.
Wait, so could you repeat your question again? I'm not sure if I'm understanding you correctly.
Maybe I so I was just wondering as to why um why you had to look through all the B's and not just the last one.
Okay, well, the maximum B, right? The last B would be equal to 1, 1, 1, 1, 1, like 15 times, right? Do you agree with that? It'll be equal to this
Oh,
minus 1.
okay. Yep.
Yeah, but that wouldn't be a valid bit set, right?
Yep.
That wouldn't be a valid placement. So we don't actually want to consider the last one.
Hmm.
Even then, remember that dp of yxb is the maximum value for up to y and x, with the final placement of the last n plus squares being b, right? So we want to actually consider every single possible placement of the last n plus 1. If we don't do that, then we might be ignoring some solutions. Okay, so for this particular example here, so it wouldn't. So okay, so let's say for this particular example, what would your final answer be? So like, how would you find the final answer to print out?
So I thought at the end we would just have the final answer in the last box.
In the last box, right? So that's
Yep.
n minus 1, n minus 1. And then what would you have here?
Oh, okay. Okay, so we're looking at all B's for n minus 1 and minus 1.
Yeah, because remember our dp takes in 3 values, right? Y,
Okay.
x, and also the placement of the final n plus 1. So we
Yep.
need some value here in order to look for it.
Yep. I got it. Yep. My bad.
Okay, great. Okay, so Jonathan says, so you sort of understand that when you look at the solution, but you want to get better at coming up with these solutions myself under time pressure. Okay, that's a very, very noble cause to be striving for. And firstly, let me clarify, which question are you asking about? Are you asking about boredom or are you asking about pebbles?
Oh, I'm not asking about any question in particular. I'm just saying in general because you asked, like, do I understand what's going on?
Right, okay. So would you say that you're asking about DP questions in general or just any question in general?
Not necessarily like DP, but I guess just in general, like I just want to try, like before, like look at the solution for anything, like even the lectures. Like I just try to like have a go myself at the problem first, and then yeah, I just try to work on the problems myself first before having a look at the solutions or like having a go or like yeah, like reading the editorials or whatever.
Yeah, fair enough. Okay, so best thing I recommend, which is just the sort of straightforward answer, is that the way you get better at doing it is by practicing it. You do a lot of similar questions and you sort of build up some experience in it. So you sort of get an intuition for how to do it. But that's obviously not always that helpful, and it's not always the advice that you want to hear. So I do have a little bit more general advice for how to approach certain problems. So one of the best ways to start is to consider your own sort of subtasks. So these, what I mean by subtasks are basically just easier versions of the question. So for example, we did it today for this particular Pebbles problem. Instead of trying to work out the full solution just right off the bat, what we did was we tried to look at other solutions as well, which might not have been very efficient, but it might have led us to a full solution. So we started off here by looking at a brute force solution, for example. Yep. And we confirmed that that was too slow, but we tried to learn something from the brute force so that we could apply it to our next question. And yeah, just a lot of questions are sort of like that as well. So you try to make some sort of easier version of the question, try to solve it, try to get some insight into that, and then try to build off of that to get to a full solution. So yeah, that would be my advice.
Cool.
But yeah, above all, it's going to be a lot of trial and error. You're probably, realistically speaking, if you see a certain problem type for the first time, you're not going to be able to solve it by yourself. So yeah, don't feel too bad if you can't solve it and you have to look at the solutions. That's totally fine, because next time you'll be just a little bit stronger.
Yeah. For this, I can't remember from this morning, but was the subtask like the DPI is the number of like the maximum score you can get from an eye by eye grid starting from the corner, and then you sort of work your way from like 1 by 1 to 2 by 2 to 3 by 3 to n by n. Is that?
Not quite. So our subtask.
Did the mic cut out?
Oh yeah, my apologies. Okay, so what we did this morning was that we looked at the final solution just right off the bat. So we went across squares one by one, and for each square, we had this sort of state here, which was the square that we're up to and the placement of the last n+1 squares. So the dp of y, x, and b would be equal to the maximum value by only placing up to y and x, with the placement of the last n+1 squares being b. So we calculate the dp values of all of those, and we use that to build up a full solution. I'll explain a little more detail. So for example, the dp of, let's give an example just to clarify. dp of 2, 2, and our b, you can sort of imagine as a sort of bit set. Let's give it 0, 0, 0, 1, 0, 0. Note that this length is n+1. Right, so this will correspond to the square would be this one. And our bits 0, 0, 0, 1, 0, 0 would look like this. So 0, 0, 0, 1, 0, 0. In other words, this dp, what this would store is the best possible score that we can get by only filling in these squares with stones and also having the last n+1 stones look like this, these 0, 0, 0, 1s. Does that make sense, at least for this particular example?
Yeah.
Right.
Because I had a few ideas for the different like subtasks, and I just wasn't too sure. Like maybe like out of all these possible different subtasks, like which one would be like the correct one to use in a DP problem. And I think I tried a few of them, or I briefly had to think about because I had different ideas for like different subtasks. and then I think, yeah, I didn't really think about doing something like this.
Yeah, for sure. This one is really hard to actually see. I'm gonna be honest, even I didn't see this. I had to ask the other tutors or the other tutors sort of shared this solution with me.
Yeah,
So
because
yeah,
I think what I tried with doing was something similar, but it was the subgroup like the rectangle starting from 0, 0 to like XY rather than all
yeah,
the rows up until XY.
yeah. So that's a good idea as well. That's a really that's a really good idea. So DP of X and Y, trying to find the best of that. But if you think about it a little bit further, it becomes harder and harder to it becomes hard to actually use this state to go to the next state. So
Mm.
yeah, it's just an example of a subproblem that has potential. It's a very good thing that you saw that, but it doesn't quite work out at the end.
Interesting.
So were you asking about like how to pick the right subproblem?
I guess so. Like, because you have like so many different possible ideas for subproblems, and then it just becomes a bit tricky to work out maybe which one you want to use.
Yeah, for sure, 100%. So yeah, there's this one, the filling in the rows and columns up to XY, which is what you thought of, which was very promising. There's like doing rows, going row by row, which is something I covered in this lesson, but not in the first one. And there's also this particular one that led to the full solution, which was a square and also the last n+1 bits. And so there's like so many different ways that you can do. You're absolutely right. So how to find it is really just trial and error. You try a bunch of different subproblems, as many as you can think of, and try to find the one that works. And also, it's just a bit of experience as well, just seeing these types of problems before and doing them. That's the only answer I can give.
Cool. How do you feel, by the way, like the content in like this course or like the assignment or the assignment questions and the contest questions? Like, how do you feel those questions compared to, for example, like Fario or like IOI questions?
Okay, I think they're easier or equal to the questions in FireIO or IOI.
Okay.
Is that, yeah, did you want anything other than just the difficulty?
No, I think maybe that was a bit reassuring actually,
Right,
because I was
right.
thinking like because like Fario is like high school level, and I'm thinking, if this is like a university level course, how much harder does it get?
Yeah, for sure. Yeah, for some reason, the level of high school is just extremely high for competitive programming. I'm really not sure why. They're really damn smart.
Yeah. Jeez.
Yeah, I'd say that the problems that we're doing are in general easier or equal difficulty to Fire and IOI. So that's good.
That's reassuring.
Mhm. Do you have any other questions about DP or the problem sets in general?
I don't. I don't know about the other students.
All right, I'll pass it around. Everyone, do you have any questions about the problem set that you like answered? All right, I'll give you guys more time to work on it then. Using a range tree to solve DP problems. Okay. Do you mean by like going through the theory or going through the coding part? Which one do you want? The coding part. Okay. Is there any reason why you want me to do a range tree and a DP? Or do you just want to know how to do a range tree? Or do you really want to know how to do a range tree and the DP together? Just a range tree? Okay, we can code a range tree. Okay, let's get our inputs. Okay, so range trees can support multiple different types of operations. So would you like a sum range tree, a min range tree, or a max range tree? I'll give the option to you. Anything's fine. All right, we'll take a max one then. Okay, the range tree is going to need to support two types of things. You need to be able to update a specific value with a new value, or update a position with a new value rather. And we need to be able to query a range. Okay, so that's how we're going to do it. So we're going to have a range tree, and let's say that the number of elements we need to store is 50. Okay. Then for a range tree, we want to actually multiply this by 4 to have enough space to store our range tree. And then we'll need to do our queries. So let's make some function signatures so we know what we're doing. In query, I'll explain what these arguments mean in a second. When I actually implement them. So just checking, Jeremy, are you familiar with how a range tree works? Like how it's supposed to work? Like how you go down the tree and how you get the range back and so on? Okay, sweet. Okay, so the way we're going to represent this range tree is surprisingly with a single array. And this single array is going to actually represent our whole tree. How do we do that? Well, I'll close my whiteboard. All right, give me a second. Okay. So let's make our range tree only store 4 elements just for simplicity. So let's say we have 1, 3, 2, 10, right, as our range tree. And so since it's a max range tree, this node's going to have 1 in it, 3, 2, 10. This node's going to store the max of these 2. And then this node is going to store the max of them both. Okay, so what we're actually going to do is we're going to represent this entire tree and all its children and all its connections in a single array. And it's going to look like this. What we're going to do is basically we're going to read across every single layer, and we're just going to put in the numbers as is. So this range tree, the root is going to start at 1, and this is kind of important. So 10, 3, 10, 1, 3, 2, 10. This is how we're going to store our tree. And one really, really interesting property about this is that the children of I, of node I, is equal to I times 2 for the left child, and times 2 plus 1 for the right child. Okay, so we can actually sort of see this in action. So let's look at this 3, for example, right? The two children of 3 are 1 and 3. So in our array, we know that the two children of this number, 3, is 1 and 3. Well, looking at our formula here, if we look at the node index 2, we multiply it by 2, we get 4, which is the left child, right? And if we multiply it by 2 plus 1, then we get the right child. So this is actually how we can get the children of an index by using very simple maths, and how we can store this entire tree within a 1D array. So does the way we store a range tree make sense so far? Great, okay. So this is what our arguments are going to represent. So in I, to represent the index that we're at. So we're going to start at 1, which is the root, and then we're going to keep going down into children in order to go down the tree in terms of nodes, right? You can imagine that we label these like this. Okay, L and R are going to represent the left and right range of our tree. And one thing that I'm going to do is I'm going to make L inclusive and R exclusive. So what do I mean by that? So this is our original array here. And we index it like this. What I'm going to do, so at node 1, the left and right are going to be 0 and 4. So in other words, node 1 covers every single node from 0 to node 4. And this is, again, inclusive, exclusive. So the 0 is included inside, but the 4 is not included. So 0 to 4, except we don't include the 4, in other words. So when we get to 2, this range is 0 to 2. This range is 2 to 4, and then so on. So each node has its sort of own range. And when we go down, when we call query recursively, we're going to go to our next I, and we're going to also update our left and right so that they're also the correct values for that particular node I. Finally, a query left and query right are going to be the left side of our query and also right side of our query. Okay, let's code this up. So let's code the query. Yeah, let's code the query first. So the first thing we want to do is our base case. So query is going to be a recursive function. So if we're at a leaf, right, we want to stop when our query reaches a leaf. We can do that by checking if L is equal to R minus 1, because you can see how every single leaf node only covers one node. If L equals R minus 1, then we just return the value at range tree I. Otherwise, we're going to calculate the midpoint. We're going to calculate the midpoint between L and R. For example, if we're at the first node, the midpoint would be 2. L plus R on 2, right? And then we're going to, if we need to check the left side or the right side. So if QL is smaller than M, that means that we want to, our range, right, is some part of it is going to be on the left side of the tree. So we want to go down there. So if QL is smaller than M, then we query into I times 2. Oops, just I times 2. That's the left child. L stays the same. R becomes the midpoint. So in other words, we're going from 0 to 4 to 0 to 2. And then our range, our query length is QL. And then QR, we'll take the min of this and M, right? So if we're going to go to the, if QR was actually smaller than M, then we still want the range QL to QM, so QL to QR. If QR is larger than M, well then this node only covers L to M anyway, so we should shorten our query just to M, QL to M. And so that will query down the left side, and we can do the same for the right side. And it'll look really similar. Go to the right child, MR. This time we'll take the max of QL and M, and then QR. And so what this is going to do, it's going to return 2 queries, and we want to take the maximum out of both of them. So we're going to start off with a best of 0. We're going to update it with the best of either of these 2 queries, if we even do them. And all we need to do is return best. Okay, so it's never going to be the case where none of these are true, because that would imply that we messed up. Okay, one more thing that I've put in is this part here. We don't actually want to recurse the leaves. What we want to do is check if QL is equal to QL and R is equal to QL. If that's the case, that means that the node that we're looking at has the same range as QL and QR. So that means that we can just return the value at that node. Okay, so to sort of quote unquote test it here, I'm going to print out, let's make max n 10. So we only store 10 nodes. So I smaller than 10, I plus plus. And what I'm going to do, I'm just going to print out the query for every single one. So the way we make a query is we start at node 1. So we always start at the root. And at the root always has the maximum range from 0 to n. I'll make n equals 10 here. And then we will make a query range. So this query range, again, as I mentioned before, is exclusive, inclusive, exclusive. So to print out the I value in our range tree, we want to print out I and then I plus 1. And finally, we print a new line. Run our program. Get compilation errors. Make sure we're using namespace std. And great, so we got a bunch of zeros, which is sort of what we expect, because when we define our range tree globally, then everything is set to zeros, right? So you can imagine that everything in here is zeros, so this entire tree is just filled with zeros. So whenever we query something, it will all be zeros. Okay, so yeah, does this query make sense so far? Okay, great. Let's move on to the updates then, because that's the only way. Printing out a bunch of zeros isn't really useful in checking if that range tree works or not. So we should probably make some updates so we can check. So let's go to update. So this one's going to be very similar. I, L, and R are going to serve the exact same purposes. But now we have a K and a V. So this will be key and value. K stands for the position that we're trying to update, the leaf node, and V stands for the value that we're going to update it to. So in other words, what our update is going to do is we're going to go down to a leaf node, we're going to update it, and then we're going to go back up and update every single node along the way. So if L equals R minus 1, which means we've reached a leaf node, then RT of I equals V. Otherwise, what we're going to do is we're going to update either the left side or the right side, depending on which side K is on. So we'll get the midpoint again. And in many ways, the query and the update function are quite similar. So if K is smaller than M, then we update the left side. So once again, we update our range. K and V don't really change. Otherwise, if K is on the right side, then we update the right side. Oops, M and R. And now that we've updated both sides, or we've updated one of the sides, we know that we have to update our own value now. So we just write RTI equals RTI times 2, or rather the max of these two. Oops, let me just rewrite that. There you go. So that's going to be our range tree. It's going to take the max of these two. Okay, let's try to see if this works. So I'm going to declare an array. And we're going to fill it up with some random stuff. That's 10 numbers, great. And what I'm going to do is I'm just going to insert every single one by one. So you can imagine that to begin with, our range tree is all zeros. Now I'm just going to update all of them. So 1, we always start at the root, and the root covers 0 to n. Our position is I, and our value is A of I. Okay, so so what this does is it's going to fill in every single part of our range tree with the value of AI, and then we're going to query every single one in order, and hopefully we should get out the array that we inputted. Great, so we actually got the exact same array that we inputted. Okay, so we want to actually make sure that our range tree works. So let's try to print out some random ranges. So let's pick some sort of range. Let's start with range. What is it? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So range 6 to 9. So the 1, 0, n is always going to be the same. And then we'll query range from 6 to 9. So the 6th element is this guy, and 9 represents the numbers from 3 to 4 here. So we're finding the max of that. So we would expect this to return 4. I'm going to put a new line after this as well, so it's actually readable. But you can see that we actually got the value 694. Okay, let's expand this range just a little bit. So we're going to go increase the range just by 1. And so we'd expect the new maximum to be equal to 9 now. So if we run this, our new query range is 9. Okay, that's pretty much covers it. Are there any more questions about this range tree and how update and query works? Sweet as. Good to hear, good to hear. Oh, for sure. I'm just curious. I could check myself actually. Does the range tree in the lectures follow the same code?
I think it looks pretty similar, except for they used addition instead of max min.
Yeah.
Or I think
Yeah.
they might have done multiple examples.
Yeah, I'm looking at it now. Yeah, it looks about similar, which is good. Okay. Because I know there's multiple ways to implement a range tree. So I was a bit worried that I might have taught a different one from the lecture slides. This is good. All right, here you go, sir. One fresh range tree.